Dear students, in this video we are going to discuss our next topic, and that is potential due to a point charge. In the last class we already have an idea about electrostatic potential at any point. Electrostatic potential at any point due to a charge. So we define this particular quantity, that is electrostatic potential at any point due to a charge or any point around the charge, as work done in bringing a unit positive charge unit positive charge from infinity to the point. Work done in bringing a unit positive charge from infinity to the point. And mathematically we have written this particular potential, let us take to the point P. If we take the point to be P, then the potential at that point is nothing but it is the work done in bringing a unit positive charge from infinity to that very point P. And mathematically we describe it as potential energy per charge. So this was our notion of electrostatic potential from our last discussion. But in this discussion, what we are going to do is we are going to describe mathematically, or describe this very electrostatic potential on its own, solely on its own, or uh, independently. We are going to define this very electrostatic potential. In this case, we have defined it in the terms of electrostatic potential energy, but now in this discussion we are going to describe electrostatic potential solely on its own. So for that, let us take a uh, charge Q, and let us take a point P where we are going to define our electrostatic potential. So in this discussion, we are going to describe this very potential at point P, which is denoted by Vp. Vp is the electrostatic potential at point P due to this particular charge, capital Q. So from our definition, the electrostatic potential at this point P is nothing but it is the work done in bringing a unit positive charge from infinity to that very point. That means if we bring a unit positive charge from infinity to the point P, then work done in bringing the unit positive charge at this point is the electrostatic potential at this very point. So what is the work done in bringing a unit positive charge from infinity to this point? So we are going to calculate that. So for that, let this particular distance, the distance of point P from the charge is, let us take r vector, and let us take, while bringing the unit positive charge from infinity to the point P, let us consider an intermediate point P dash. That means we have brought slowly this one unit positive charge from infinity. So while bringing it from infinity to the point P, we come across a point, an intermediate point, and which is represented by P dash, and which is at a r dash vector. So r dash vector is the position vector of P dash, and r vector is the position vector of P. So firstly we are going to see what is the force experienced by the unit positive charge while it is at some intermediate point P dash, which is at a distance of r dash. So force experienced at P dash will be our this 1 unit positive charge will experience a force due to this our source charge, that is plus q. So what is the force according to Coulomb's law? Force will be 1 by 4 pi epsilon naught this charge, magnitude of this charge into magnitude of this charge divided by the distance between them, that is 1 divided by 4 pi epsilon 0 if it is free space. This charge is capital Q from Coulomb's law, and this charge has a magnitude of 1 because it is a unit magnitude or unit positive charge divided by the distance between them. Now the distance between them is nothing but it is r dash square. So according to Coulomb's law, this unit positive charge will experience a force at particular point P dash as 1 by 4 pi epsilon naught Q into 1 divided by r dash square. Now let us assume that uh, we are bringing this unit positive charge very slowly towards the our final point P. So while doing so, let us consider a very small displacement along the point P. That means we have considered a very small displacement while bringing this charge from P dash to P or from infinity to point P, and that is represented by some del r dash, and which is directed towards this direction. So del r dash is directed towards this direction. Our r dash and r are directed opposite to that. So what is our work in displacing this particular unit positive charge by a displacement of del r dash? So that is we are going to calculate. So work done in displacing the unit positive charge by let us say del r amount. So if we displace this particular charge by del r amount, then we need to do some work against our repulsive force, because this 1 unit positive charge will experience a repulsive force along this direction. So we are doing work in this direction. We are doing work against this particular repulsive force. So in doing so, we are displacing it by an amount of del r vector, which is opposite to the r vector. That means, so in displacing a unit positive charge by del r, so we need to do del w amount of work, and that work is nothing but it is the force at this point, the very point, the force at the particular point, and the amount you are displacing it, because force into displacement will give me the amount of work. So force we have already calculated, 1 by 4 pi epsilon 0 q into 1 divided by r dash square, and the amount of displacement we have done. So if you look very carefully here, our r vector is directed towards this direction, but our del r vector is directed towards this direction. So directionally they are opposite to one another. That means our del r is actually have a negative direction. Actually it has a negative direction if r vector has a positive direction. So that particular negative sign, because del r is directed towards negative direction, so that particular negative value of delta r we are going to show it here, just to understand that we are displacing it not toward the direction of r dash or direction of r, but opposite to that. So this displacement and this r dash are opposite in direction, so that's why I have given one negative sign out here. So I'm just repeating it. So delta w is 1, but now negative sign. Okay, I'm writing it with negative sign. So delta w will be, if I bring this negative sign in front, it will be negative 1 by 4 pi epsilon 0 q into 1 divided by r dash square delta r. So this is the work done. This is the work done in displacing this unit positive charge against this particular electrostatic force by an amount of delta r, isn't it? If we displace it by amount of delta r vector along this direction, then we get this amount of fear, or we have to do this amount of work to displace it by amount of delta r. But our here sole intention is, what is the work done in bringing a unit positive charge from infinity to the point. So my intention is not to calculate the work from by displacing it by amount of delta r. My intention here is to calculate the total work done in bringing this unit positive charge from infinity to the point P itself. So if I add all this kind of small work from infinity to the point P itself, then we are going to get the total work done. This is the only some small part of the work done by displacing it by delta r amount, but actually we are displacing it from infinity to the point P. So if I integrate this small amount of work from infinity to the point P, then I'm going to I'm going to get the value of the net work done. So the net work done in bringing the unit positive charge from infinity to the point P is W is equals to, if I integrate this delta W, now I am bringing this particular unit positive charge from infinity to the point P, and to the point P means it is at a vector r, so it is at a distance of r. Infinity is at a distance of infinity, so from infinity I am bringing it to this point P, which is a distance of r from this charge q. So I am bringing it from infinity to the point r. So the net work done will be infinity to the point r. So delta W we have already calculated the small work done, displacing it by this delta r amount. So it is minus 1 by 4 pi epsilon 0. Q into 1 is this q divided by r dash square. And for small displacement, this delta r can be converted into dr. So negative sign comes outside. So infinity to r 1 by 4 pi epsilon 0 q by okay, this displacement is, let us take, rather taking it delta r, let us take it to be, excuse me, delta r dash. So make delta r as delta r dash so that it match with our r dash. So make all the delta r to be delta r dash. This is also delta r dash. Okay. So this is also delta r dash. That becomes, this is dr dash. So q by r dash square dr dash. So now integrate this quantity inside the bracket. It becomes work done is equals to minus infinity to r. Okay, let us take constant outside. Minus is constant which comes outside. Q is constant. Q by 4 pi epsilon 0 is constant. So infinity to the r. So this 1 by r dash square dr dash, which is a variable here. So if you integrate it, you get minus q divided by 4 pi epsilon 0. What is the integration of this? Infinity to r. Integration of this is, okay, this is r. If I take above or reciprocal it, I'll get r dash minus 2. It is r dash square in the denominator. It is r dash minus 2 in the r dash to the power minus 2 in the numerator. So if you integrate this, what you'll get? You'll get simply root done is equals to minus q by 4 pi epsilon 0 infinity to r. So this is r dash minus 2 plus 1 divided by minus 2 plus 1 dr dash. or work done is minus q by 4 pi epsilon 0. So this is your r dash minus 1 divided by minus 1 dr dash. So minus 1 comes outside. So that minus and this minus get cancelled. So it is work done is equals to q by 4 pi epsilon 0. Okay. After integration. So after integration, it is this much. So it is infinity to r. This is my infinity to r. So minus comes outside. So this minus and this minus gets cancelled. This is r dash minus 1 from infinity to r. So this after integration we get this one. The integration of this much is this much. So integrations get out from the sum. Okay. So next step is w is equals to q by 4 pi epsilon 0. So replace r dash by r. So it is r minus 1 minus replace this r dash by infinity. It is infinity itself. So okay, infinity minus 1. Let us take power is minus 1. So work done is q by 4 pi epsilon 0 1 by r minus 1 by infinity, because r minus 1 is 1 by r, infinity minus 1 is 1 by infinity. Now 1 by infinity is 0, since 1 by infinity is 0, because infinity is very large number. If you divide 1 by very large number, it comes out to be 0 approximately. That means your work done is q divided by 4 pi epsilon naught into r. So this is your total work done in bringing a unit positive charge from infinity to the point P. So if you bring a unit positive charge from infinity to the point P, then you need to do this much of work done. And this work done will be stored, or this work done itself is the potential at the point P, that is Vp. So Vp will be equals to Q divided by 4 pi epsilon naught into R. So the potential at any point around this charge Q is given by this relation. So it depends upon the distance at which you are bringing the unit positive charge. So at nearer distances around this charge, R will be less. If point P is nearer to Q, then R will be less. That means Vp will be my large. That means around any charge, suppose you have a charge this way. If you are bringing this very near from infinity to the point P, which is very nearer to the charge itself, then this distance will be less. This R will be less. So if this distance is less, then potential will be more. That means around this charge or nearer to this charge, the potential will be high, and farther from this charge, this distance will be large. If I take another point P, or let us take another point Q, or let us take another point R, which is farther from the charge, then this R will be large for that point. That means if R is large, the potential at that point will be low. So if you move away from any charges, it's the potential at those points will be keep on decreasing. So potential around any charge will be large if the points are nearer to the charge. So this is it for today. Thank you.